Hello, everybody. Let's get busy. I sent you an email this morning. Don't worry if you didn't look at it yet. We're going to be working on this problem for at least a half hour. It's a little larger than the problem that you will find on your test, but this is the exact same layout as you will see on your test. So what we have right now is a molecule with the formula C17H23FO2. It gives an intense infrared absorption at 1719 reciprocal centimeters. And that piece of information says but one thing, and this is all we need to know about IR. If I can get my pen to work, it's Monday. There we go. There's a carbonyl present. Carbonyls absorb that frequency of infrared radiation. That's good. That's a good piece of information. This right here is another piece of information that simply says one thing. Simply says my molecule possesses either oh yeah, an alkene or an alkyne. If you look at chapter 6 for alkenes and chapter 7 for alkynes, you'll see we studied the reaction of bromination. Please, this is only a solvent, so don't try to make that part of the product. This would make a vicinal dibromide with each pi bond. Now, in terms of index of hydrogen deficiency, IHD, we have a molecule that's C17H23FO2. That corrects to this formula C17H24, keeping in mind that a halogen replaces a hydrogen. And I have corrected the formula to get rid of the halogen, and oxygens are ignored because they do not change the number of hydrogens. The parent molecule that has 17 carbons and no IHD, which means there's as many hydrogens in the formula as possible, is C17H2 times 17 plus 2 is 36. We have a difference of 12. Remember, IHD is pairs of hydrogens. So our IHD is 6. We already have 2 of these IHD items accounted for. We have the pi bond in a carbonyl, and we either have the pi bond of an alkene, which would give an IHD of 2, 1, 2, or an alkyne, which by itself has 2 pi bonds, which would increase this number to 3. So we'll narrow this possibility down in like 15 seconds, because when I see data in the delta 7 region, which I see here, this means but one thing. When we have peaks at 7 ppms, we're talking about a benzene being present. And if you're not sure about that, then I just direct you towards tests. And I have a test handy here. I just forgot where I left it open, so I'll open it. No, I don't want that one. There you go. Coming up, I'm going to look at the first page or the second page of a test. Yeah, I've got an answer key here, but that doesn't change it. It's the second page. And we see on the second page that we have benzene, typically 6.5 to 8.5, but a normal benzene's right at 7.1. So if you see peaks near 7.1, that's what immediately you start thinking of, benzene. That is an IHD machine. If you have one benzene in your molecule, I got the bond straightening tool on here. If you have one benzene in your molecule, IHD is 4. 3 pi, 1 ring. So we've got it narrowed down to carbonyl for IHD of 1, alkene for IHD of 1, IHD of 4, the total is 6. We cannot have an alkyne. That would have an IHD of 7 with all this data we have going on here. That's good news. Now, as soon as I also see a benzene, I got to ask myself how many H's are on the benzene, and the answer is 4, which means there are 2 groups on benzene. And the patterns will tell us the orientation of the groups on benzene. You may have seen in other videos, other videos on spectroscopy, that we have disubstituted benzene that can be ortho, meta, or para. And that just means if you have one group already on benzene, then ortho would be here, and meta would be either here or here, and para would be straight across. So we have 2 groups on benzene as indicated by 4 hydrogens. We have meta substitution, oh, the miracle of looking at the problem ahead of time. This would be a singlet on benzene, that is L. The 2 doublets on benzene could be either I, K, or reverse those. And we have J left, and definitely J would be a triplet here. And I will explain that very briefly. These are H's, by the way. H's. Okay, that H didn't work out very well there at all. Okay, this would be a doublet because it has one neighbor called J. J would be a triplet because it has neighbors called I and K. K would be a doublet. It has one neighbor called J. And L would be a singlet. It has no neighbors. These are groups that are not hydrogen. They are not hydrogens, so they do not add to the number of neighbors. We got a lot of points already. Do you believe we have 8 points out of 24 now? Yeah, if you just had this on your test with proper labels, I, J, K, and L, I'm going to give you 8 points. So partial credit is something that you definitely want to shoot for. I then, when I solve these problems, and there's no one right way to do these problems. You could have solved this problem without carbonyls and alkenes information being used and come up with that later because they're going to show up in these peaks here. But I personally prefer to go for strange things like that next. And let's just have different color for that. 6 H's, all the same with no neighbors. Let me repeat. There are 6 H's of the type D. They have no neighbors because singlet means 0 neighbors plus 1, singlet. So right now, I know that D has CH3 identical to another CH3, and quite often they're attached to the very same thing, and that's one way to make them identical. And if there's no neighbors, then this next C has no H's. Now your question is, how can you get that peak up to 2? Well, if this was a carbonyl, that peak, I'm looking at the chart here, a carbonyl, let's see, it's a little high. It would be 2.2 or 2.4. Clearly not 2. What about up here? Just C's and H's. 2.0 seems to be in the middle of this region here called allylic. It seems like it might work. Why don't we go with that and see if we can do the rest of the molecule? So if C that's black here is an alkene, and we know we need an alkene, and alkenes often have hydrogens on the alkene. This is my thought process here. If they're one of the positions here or here, there's two positions available, is an H, where would it show up? That question's answered by going back over here. No, it's not there. It is there. Alkene H's, there's two varieties. There's the internal alkene down here, around 5.3. And there's the terminal alkene. That means it's at the end of a chain, 4.7. I think the first one fits better. Internal alkene hydrogen 5.3. 5.3, doublet, 1H. One alkene hydrogen. This down here could be an alkene, but we're told it fits into two categories. So if it's an alkene and anything else, it's going to go outside of the alkene category. So I'm not thinking alkenes for that 5.7, even though it's real close. I'm thinking alkene right here for 5.3, and it's a doublet. That's a useful piece of information there. And I didn't label my D here. If you don't put these labels on, you're risking half credit. Yeah, you're saying these are D. Now I'm going to say that this one right here is G. You're not going to get credit for G until you fill out all three, until you have it fit all three parts here. We've got the 5.3 fit. We've got the 1H fit. As long as I don't put an H here, that would be two H's the same, and our molecule would be done, so it's clearly not a good idea. And we don't have the doublet fit. Doublet means this next C has to have an H because this neighboring C has no H's right now. So we need one H on this carbon right here. We'll worry about what that H is a little later. So if you leave it like this, you're going to get full credit for G, 2 more points. What options do we have for that blue H? Neither one of these can be an H, or else this would become a triplet or a quartet. So the blue H, not on benzene. We've accounted for all the benzene H's, so these ones are gone. I love how this works. The neighboring blue H, I'm going to call H, sorry, H. The H called H. See, there's one of them. And there's a reciprocal relationship here. This 1H has one neighbor, and it's G. Sorry, we're talking about this 1H having one neighbor on one side. I haven't even explained what D of T means. Some of you may have read about it. It's real useful information. Some of you would maybe prefer starting with this information. Let me break it down. The blue H has one neighbor on one side causing a doublet. 1 + 1 gives 2, which is doublet. On the other side, another carbon has two H's causing a triplet. Useful information. Let's do a CH2 and we can figure out what that CH2 is a little later. You now have full credit for H. It's a doublet on one side and a triplet on the other. Why do we see such things where there's a pattern of patterns? When the neighbors are very different chemically is when you see that. This is a vinyl H attached to an alkene. It's vinyl. This is not vinyl, which makes it a different category. They have different influences on H. They're treated almost individually. And it's the better machines that can give you these. Cheaper machines would just be a messy looking peak. You might not even be able to make out patterns. All right. So we have two H's here. We've got lots of possibilities for it. It could be C, it could be E, or it could be F. So our point count so far is pretty handsome. We have 2, 4, 6, 8 over here, 10, 12, 14 here, 14 out of 24. You've already passed this question and you haven't even come up with the molecule yet. I'm going to focus next on carbonyls, because when I see carbonyls, I often think about that new alpha we learned about the other day. If a molecule has a carbonyl, there's a high chance it's got a carbon attached to the carbonyl. That's called an alpha carbon. So let's copy a carbonyl down here. Just a different set of thinking down here. And if we have an alpha carbon with an H, where would we expect to see that? We would expect to see that alpha carbon with an H somewhere between, well, the lowest would be 2.1 and the highest 2.6. And let's see if we have one of those. Lowest 2.1, highest alpha. 2 is a little low and we've already accounted for it. 2.3 fits right in the middle and this is a little high. So this 2.3, we're going to call E. I'm going to pause the video for 1 second to make sure all the data for E is correct before we proceed and confuse ourselves with a bad piece of data. I'm going to stop the share. I'm going to pause the video. So I'm just, and hopefully you don't get to see the answer to the question here when I'm messing around. All these programs. Here we are. Okay. It'll be a second. My program wasn't open. And I'm looking for E. And we have E, E, F, G, E. There's only one H called E. That is a mistake. So let's go fix it. Sorry if you were going with the email this morning. That would have caused you a bit of a nightmare. And I got things to do here. This is going to be hard for me keeping track of all this stuff going on. Video is here. Starting video. Sharing screen. We found a mistake in E. Well, I found it, but some of you may have found it already. E is supposed to be 1H. 1H. So we drew the 1H. I'm going to correct it on the previous page too, where we have the original. This is so you can practice here. 1H. And there we go. So we have 1H called E, and it's at 2.3 because it's alpha to a carbonyl. It's a sextet, which is a lot of good information. How can you have a sextet? Well, you have 5 neighbors, clearly. And 5 neighbors, when there's only 2 spots available, is most likely going to be a CH3 for 3 neighbors and a CH2 for 2 more. And let's see if we can make something fit from that. This here would be 3 H's with a doublet pattern because there's only one neighbor called E. The only 3H doublet I see is B. Let's call it B. Racking up 2 more points. And let's do a little inventory, see what we've already accounted for. B's done. A we haven't done yet. We did E. We did all of the benzenes. And what else have we got? We got G and H. So what we have left is two H's for F or two H's for C. Why am I talking about two H's? Well, this is two H's. I'm leaning towards, well, I'm not leaning either way, because this right now, as it's written, would be a doublet here. Okay, and right here, doublets present and doublets present. Now, how do you make this correct? You'd need no more neighbors on the other side, keeping in mind we have one more position to fill. One more position to fill right here. And that can't be an H, or else this would be a CH3. We need two H's to make the E triplet of quartets correct. Or sorry, sextet, sextet. 3, 2, 5, plus 1 is 6. I'm thinking about a CH3 just to see what happens, because I saw something ahead of time. This would be a 3H triplet. I'm liking it for A. Even if it's the wrong answer, it gets full credit. And then now we have a doublet of quartets for C. And that's a good chunk of the molecule that's done. Everything here fits. Let's cross things off because I think we're almost at the end. Let's see, we did A, B, and C. A, B, and C. We just have to do D, we did already. 6H is all the same. Thank you for not interrupting me to point that out. I eventually caught myself. And F, we have F unavailable for comment. 2.7 doublet, 2 H's. Interesting. We also have another O to account for. I'm going back to the original formula. And I believe we just have a C, 2 H's, and an O left over. And an O. Yellow doesn't show up very well. Okay, well, we've got a CH2 on the page already. Somehow we have to make that work for F. F. H, 1H, F, 2 H's. F has a doublet pattern. So we've got that. We never worked on, we never can get full credit for H yet. We didn't get it to be in two categories. I was a little hasty there. How can we get H to be at 5.7? And how do we get F to be at 2.7? It's a good question. Okay. Well, one category that H could fit in, keeping in mind we have also not accounted for the F. So we got to come up with those guys. CH2's up here. O remains to be seen. F just showing up on the scene here. That would bring it up to 4.5 if you look at the chart. 4.4 to 4.5 if there's an F. We need to bring it up to 5.7. That's another jump of 1.3 or thereabouts. Oh, it's already done. Being allylic brings it up. So if we're going to do H right here, it's in two categories as it says. And if you're doing this problem on an exam and it fits two categories, I will tell you it fits two categories. Otherwise, these problems are already hard enough. Okay. So let's see if the 5.7 works out. Baseline category for nothing special on H would be a C with one H. Doing the baseline on H. HCR3. I believe 1.5 fits that up here. 1.6, I'll call it 1.5. Stick with my gut. And that's 1.5. And then we're going to see what happens when we're putting RCH2F. RCH2F. Okay. .5, that's a bump of 3. And another category being allylic. And that takes it up to, let's call that 1.8, 1.9. That's a bump from 1.5 to 1.9 plus 0.4. So we're taking the something that started at 1.5, bumping it up 3 for being on a C with an H, F, sorry, a fluorine. And we're bumping it up 0.4 more. So 4.5 for 4.9. My intention was for this to be the correct H. So on exam day, when I'm not making this thing up 20 minutes before class or a half hour, I would have had a better number there, a little lower. Unless I did something wrong here. We can talk about that later, some video correction or something. So H worked out not ideally, but it's in 2 categories, so it bumps up to higher than 4.5. I did good math there, and I did good math there. Okay, we're left with the fact that F is not entirely done. It would not be at 2.7 unless there's something present, like a phenyl, making it benzylic. Let's make sure 2.7 would work nicely for F, and F is a doublet because it has one neighbor called H. And here we go, benzylic 2.7. That one fits perfectly. We're left with just an oxygen. We've accounted for the CH2, we've accounted for the fluorine, and we haven't put the oxygen. There's no room for an oxygen here. There's no room for an oxygen here except here. And this then has to be the second group on the benzene. We can draw our whole structure with that information. I'll try to do it neatly down here. So if one of the groups is here with the O, then the carbonyl, then the C with a CH3, CH2, CH3, and CH3. We'll put the letters on here in a second. And the other one is the CH2 going to a C that has an F, goes to a C double C with 2 C's, and we'll put the letters on in orange. Oh, don't know how that happened. And letters, just to finish up here, we have the 2 CH3s called D. We have the vinyl called G. We have the H here. We have the 2 CH2s called F. And let's see. Let's go over to the carbonyl. We called alpha the E. The CH3 was the B. The CH2 was C. Connected to CH3 called A. And in the benzene area, The ones closest to oxygen, the electronegative atom, should be the two highest, 7.5 and 7.6, because of inductive effects. The singlet has to be here, L. No neighbors, K close by as well. And these are interchangeable pretty much. I'll pick the one closer to O to have the slightly higher number. And I would be the last one. J. Yeah, that would be a triplet. And well, we don't have a choice. Sorry. We didn't do I, which would be a doublet. No choices. This has to be the doublet. This has to be the triplet. That is our molecule, and you deserve a break, and so do I. So we're going to stop sharing, and we're going to end, and I'll see you in 5 minutes.